10-minute Q&A. And yeah, I will choose a 2 or 3 questions from chat box, or if you can question, you can just unmute it and ask some question. So enjoy the talk. So here I will stop my sharing the screen. So Professor Li, you can share your screen when you're ready.
Okay, thank you, Professor Xin, for the nice introductions, and also thanks for the invitation. Just let me share my screen.
Sure.
Yeah, can you see my screen?
Yeah, perfect. Perfect.
Okay, yeah. Okay, my talk today is rate splitting multiple access for the Internet of Vehicles, federated edge learning, and platform control. So basically, in this work, we try to do the joint communication, computing, and the control design for the Internet of the Vehicle applications. So communication here, we use rate splitting multiple access, RSMA. For computing, we use federated learnings. For the control, we use a model predictive control to control the vehicles in a platoon control in Internet vehicles. So basically, the reason we use RSMA is for this problem, we know RSMA can broadcast the common message to all the vehicles. Also can, at the same time, can also unicast private messages. So we use broadcast message to broadcast the global models in the federated learnings. For each private message, we send from control centers to each vehicle to control each vehicle's the status. So the work is jointly done by Shengyu Zhang, Dr. Shiyao Zhang, Dr. Weijie Yuan, and Professor Lajos Hanzo. So this is a talk is based on the recent work we submit to the IEEE CSIG special issue on RSMA. So this is the outline. It includes the 4 parts. First, give very brief backgrounds on the evolution of communication technologies and several multiple multiplexing techniques, including RSMA. And then we introduce the potential application of RSMA in the Internet transportation in RTS. So what's the motivation for using RSMA in RTS? Then we introduce our proposed RSMA-based Internet vehicle problem. Then we show some of the key system models, problem formulations, and some results. Then we conclude my talk. So we're all familiar with this evolution of cellular network from 1st generation to the 5th generation. For 1st generation, basically it's analog communications have very low data rates to support voice communications. For the 2nd and 3rd generation, so the multiplexing scheme is basically the TDMA or CDMA. For 2nd generation, it's narrowband TDMA, narrowband CDMA or TDMA. For the 3rd generation, you see I use a wideband CDMA. So data is for 2nd generation 50K bps. For 3rd generation, for 3G is 3 megabits per second. The 4th generation LTE, the data rate increased to up to 300 megabits per second. The key multiplexing scheme is OFDM. For 5G, it's also use OFDM. Also, maximum MIMOs also introduced now also going to multiplex NOMA in 5G. So as we just discussed before, there are 2 types of multiplexing protocols. One is orthogonal multiple access, OMA, like TDMA, SDMA, or OFDMA. And in addition, the 5G introduced now orthogonal multiple access NOMA in order to improve the access spectral efficiency to support more number of users. So for SDMA, so basically, the base station do the linear precoding at the transmitter side to form the multiple beams. Each beam point to 1 or more users. So basically, the different users are separated covered by different spatial streams. Since the different users use different spatial streams, So we can use the same frequency across all the users. So advantage of SDMA is they can explore the spatial multiplexing benefits of the multi-user MIMO channel under the perfect CSIT, CSI channel state information at the transmitter side, and also had the linear precoder and the receiver complexity. Disadvantages is designed for unloaded regime. Unloaded regime means the number of users is limited by the number of antennas. For them, if you have 3 transmit antennas, you can only form the 3 spatial streams. So it's not work for the overloaded the region. And also it only achieve the optimal DOF with the perfect CSIT. If you have an imperfect CSIT, when you do these linear pre-codings, this will cause interference across different users. And the second multiplexing, commonly used multiplexing is OFDMA. So basically use the overlap subcarrier, but these subcarriers are orthogonal to each other's. To different subcarrier allocated to different users. So advantage is receiver complexity is low. Disadvantage is same as SDMA. It's also designed for unloaded the scenarios. It means the number of users is limited by the number of subcarriers. And to increase the number of access users, so 5G propose non-orthogonal multiple sites. Non-orthogonal multiple sites means for each channel in the orthogonal multiple sites, for each channel at any time, each channel can only allow 1 user to transmit. For a non-orthogonal multiple sites means at any time, there could be 1 or more users can be transmitted on 1 channel. So there are 2 main streams of norma. One is the power domain norma. Power domain norma basically use different power level to accommodate different users. Second is the code domain norma, like RSMA, basically use different subreading codes to separate different codes. So this is a power domain norma. The idea is very simple. So it's designed when the users are distributed spatially differentiated. Means do you have a near user or far users? For example, user 1 is a near user, close to base stations, and user 2 is far users, is far away from the base stations. So in order to ensure the impartiality in terms of achievable rate, so we allocate less power to the near user and more power to the far users. So this means user 1 will be allocated with the low power, and user 2 will be allocated with the more powers. So this is a basic idea. We use a different power level to distinguish different users. User 1 allocated with the low power level, user 2 will allocated with the more power levels, higher power levels. So at the user 1, then we use the successful interference consolations. So we first recover user 2 signals by treating user 1 as the interference as a noise to recover user 2. Then we subtract user 2 signals, then we can get user 1 signals. So this is at user 1. User 2, so basically just treat user 1 as a noise, then can recover user 2 signals. So this is a norma. So norma basically can deal with the overloaded region. Overloaded region means the number of users, it could be more than the number of the orthogonal subchannels. But it's mainly designed when the user locations are spatially differentiated, means you have a near user or far users. So the disadvantage is only effective for the case when there's far users or near users. They are spatially differentiated, and they are not designed for general settings. Also, the receiver need a successful interference consolation complexity is high, linearly increase with the number of users. If you have 4 users, so you need a 4 level successful interference consolations. So complexity will be linearly increasing with the number of users. And so all the previous they mentioned the multiplexing orthogonal or non-orthogonal multiple sites. They are the special case of rate splitting multiple sites on RSMA. So for RSMA, basically, so this is a general structure of RSMA. It includes the common message and the private message. They also transmit in a power domain. to multiplex the messages. So this is a one layer RSMA. So each user has a private message. So for example, you have a K users. W1P is a private message for user 1. WKP is a private message for user K. Then each user also has a common message. The W1C is a common message for user 1. WKC is a common message for user K. Then you combine all the common message of all K users into one data stream. Then you transmit this in one common data stream. The common message W1C or WKC, the common message of all users will combine into one data stream. Then will be transmitted through one common data stream. Then all this one common data stream and the K private data stream will be transmitted at the transmitter side. At the receiver side, we first decode the common data stream by treating other message as the interference. This is the successful interference consolation, same as the norma. Then we subtract the common message from the received the signal. Then we decode the private streams. So so this relationship, so SDMA, norma, or other multiplexing are the subsets of RSMA, just special case of RSMA. For example, for SDMA, there is no common message. So user 1, user 2 each transmits its private message. For norma, so user 1 transmits its private message, and the user 2 transmits the common message, W2. For multicasting, no user transmits private message. All the users just transmit the common message, W1, W2. So W1, W2 will be all decoded by both users. So this is a general setting for RSMA. So it includes each user, it has its own private message, W1P, W2P, private message for user 1, private message for user 2. And also have a W1C, W2C, and that's the message transmitted in the common data stream. That's the user wants the message transmitted in the common data stream. This W2C is the user 2's common message transmitted in the common data streams. Okay, so these two information will be decoded by both users. So this is a general structure of RSMA, which include all the previous, the orthogonal multiple sets and non-orthogonal multiple sets as a special case. So this compare the different multiplexing schemes for normal multi-user linear pre-coding, like that's SDMA or RSMA. So we consider user deployed the scenarios. For norma, it only works for aligned channel directions. Aligned channel direction, because for norma, the users they superimposed in the power domains. So there has to be aligned falling in the spatial stream. They have to be aligned in the channel directions. Also, the users has to be spatially differentiated. As I mentioned before, they have a larger disparities in the channel strength. They have a new user or far users. And for multi-user linear pre-coding, that's SDMA, they work for unloaded network. For RSMA, it works for any settings, any load or any angles. So it's very general. For decoder structures, for norma, for multi-users, the multiplexing in the power domain, norma to support the multiple users in the power domain. So they need a multi-layers SIC. So the complexity linearly increases with the number of users. For multi-user linear pre-coding, you don't need SIC. The pre-coding is done at the transmitter side. For RSMA, you only need a single layer SIC. That's to separate the common data stream and the private data streams. For CSIT requirements, for norma and SDMA, you need accurate CSIT. For RSMA, it's more robust. It's not very strict requirements on the CSIT. Yeah. Now, let's look at the potential application for RSMA in the ITS. ITS means Intelligent Transportation System. So basically, ITS, Intelligent Transportation System, is joint design of communication, sensing, and the control. For example, for the traffic flow management, to control the traffic light, control the traffic flows, also used for autonomous driving, for incident management. The aim is to ensure the safer, more coordinated and smart use of transportation network. And one key element for intelligent transportation system is IOV, Internet of Vehicles. That's the wireless communication between the vehicle and the vehicles, we call the V2V, or communication between vehicle and infrastructures, we call the V2I, or vehicle to everything, called the V2X. There are several challenges in designing wireless communications for ITS, for Internet of Vehicles. First, for Internet vehicles, the motion of vehicle is highly dynamic. So the network topology is vary with the time, it's very dynamic. Also, each vehicle's the private status, like moving speed, locations, the height, angles, all these are private informations. So this should not be disclosed to all other vehicles. There's a privacy concerns of transmitting this, sharing this information in the network. Also, each vehicle has used the battery to power, has a limited the budget. You can't do very complex the processings. So this is a general structure of IOV in ITS. So you have autonomous vehicles. Then the transmitted through the IOV, through the Internet vehicles, vehicle to vehicle or vehicle to infrastructure communication infrastructures to transmit the status or the traffic condition of the roads to the control server. Then each local control server then transmit feedback this local the traffic information to the global control servers. Global control server then transmit the global traffic information to the local control plan. Then based on this information, local control plan do the control to control each vehicle's the speed, height angles or the accelerations and so forth. And the current IOV use orthogonal multiple size. However, orthogonal multiple size is not efficient for IOV. As I mentioned before, for orthogonal multiple size, the number of users is limited by the number of available channels. For Internet vehicles in the future, Internet vehicles will be a huge number of the vehicle on the roads. So the orthogonal multiple size basically limits the number of the users which can be accommodated in the communication network. Due to this reason, it's also caused a long delay in the scheduling because they only have a limited orthogonal the channels available in the network. For non-orthogonal multiple size, it's also hard to implement in the IOV. As I mentioned before, in order for non-orthogonal multiple size to be used, so you must have the channel has to be spatially differentiated. You have near users or far users. For the Internet vehicles, because the vehicles locations they are varies with the time. So maybe this don't have such in the network don't have such differentiation in the spatial locations. Users maybe are clustered together, so they don't have a near user or far users. Also, the processing complexity is too high. You use successive interference cancellations. Also, NOMA is very sensitive to the CSIT. For Internet vehicles, vehicles moving with at a very high speed, the channel estimation, accurate channel estimation is quite challenging. So this shows the advantage of RSMA for potential application in Internet vehicles. For Internet vehicles, basically need to support a hybrid transmission traffic, need to transmit not only the broadcast information, also private messages. I'll talk about this shortly. Also need to support high mobility. High mobility make channel estimation very challenging. Also has to be high reliable and low delay tolerant. So RSMA can meet all these requirements. So this is a key challenge for designing communication system in IOV. First, as I mentioned before, you need to estimate the channel state information at the transmitter side. For high mobility scenario in the Internet vehicle, make this transmission more challenging. Also, in the Internet vehicles, you need to transmit not only the broadcast message, also private messages. Also, each user's each vehicle's the private state is private information. You don't want to share such information through the net over the communication network. So overcome this problem. So in this work, we try to combine jointly design communications, computing, and the control to tackle all these challenges. The communication, we use RSMA. RSMA, as we mentioned before, can transmit common message, which is broadcast messages, also private messages. So basically, the common message can be used for global model training in federated learnings, and the private message can be used to control each vehicles. And the federated learning, computing, we use a federated learning. So each vehicle only transmit the trained models, like the gradients, instead of transmit the raw information, state of each vehicle's the private information. We only transmit the trained models. So this can preserve the privacy of each vehicles. Control is mainly to control each vehicle's the moving status, its hiding angles, accelerations, and the speed, and so forth. So we jointly optimize the communication, which is RSMA, computing, which is federated learnings, and the control to overcome this problem to ensure the safe operation of the vehicles in the transportation network. So this is what I mentioned, the integrated communication, computing, and the control. For computing, we use federated learnings, which provide the privacy preserving distributed learning for the control system. Also, through the federated learning, we can reduce the processing time, the model training time of the entire system. Communications can ensure the safety operation of the vehicle control, can also reduce the latency for onboard computing. For control, can guarantee the safety distance between any two vehicles, and ensure enhanced dynamic vehicle moving operations. So this is the block diagram of the systems. Each vehicles collect its local model, then through V2X communications, upload these models to the control servers. Then control server collect all the local model, then aggregate all the local model to the average, then calculate the global model, then through V2X communications, broadcast the models to all the vehicles. At the same time, also transmit unicast the private control information to each vehicles. So here we use federated agent learning, for short, we call the FEW for short. FEW means federated agent learning. So here we consider a scenario of platoon control. Platoon control, you have a leader vehicle, which is treated as the agent server, train the global model. Then each follower vehicles is treated as the agent nodes, which upload its local gradient to the leader vehicle to update the global models. So through federated learning, instead of uploading the private data of each vehicles, so here each vehicle only upload the trained data. So this can preserve the privacy information of each vehicle. So this is the general process, the block diagram. So each the leader vehicles receive the information from the follower vehicles and the base stations, and then compute the control input for the platoon and also the global model for the field. Then after aggregate all the local models, the leader vehicle will calculate the global model, also calculate the control information for each follower vehicles. Then transmit this broadcast the global model to all the vehicles, and then unicast private information to each follower vehicles. Then each follower vehicles receive the control input, also the global model for the leader vehicles. Then train the individual local models based on the receive the global models. Then upload the relevant information to the leader vehicles. So this is the edge federated learning models. So for each local vehicles, we train the local model through the local data sets. So BI is the ith part of the training samples. So here FWI is the loss function for the ith part of the training sample. And FKW, so we aggregated all the local training samples at a vehicle K. We average them together. Then we calculate the local loss function for the vehicle K. Then we upload the local gradient of the local model to the lead vehicles. The lead vehicle will do the average all the local gradient, then update the global models. So here we consider non-orthogonal unicasting and multicasting enabled RSMA. As I mentioned before, for unicasting and multicasting enable the RSMA. Basically, multicasting is broadcast the global model to all the vehicles to enable all the vehicles to update the local models. Unicast is the lead vehicles will unicast a private message to each local vehicle for control each local vehicles the status. So this is the C0T is a broadcast message which broadcast to all the vehicles, and the CKT is a portion of the message in the common data stream transmitted to the case vehicle. So C0T, as I mentioned before, is a broadcast message to all the vehicles, and the CKT is a portion of the message transmitted to case vehicle in the common data stream. So they together the sum is equal to the achievable rate of the common data stream. Okay, so C0T is the data rate for broadcasting message, and the CKT is the data rate of the message for the case vehicle in the common data stream. So to add up together is the achievable rate of the common data stream. And the unicast message for vehicle K basically include the port message transmitted in the common data stream CKT. Also, it's a private message transmitted for the vehicle K. So this is what I mean for non-orthogonal unicast multicasting based RSMA. So we unicast message for control input to control each vehicles, and also broadcast the global models to all the vehicles. And for edge learning in the planning stage, it's the global model mainly is used to determine the path vehicles, or to avoid the collision using the global models. So how we train this the model is we train during the control stage. We basically follow the control input, receive the control input from the lead vehicles, and then based on the current the locations, position, the speed, acceleration, head angles, then we calculate the control stage. So we use this to train the global models. So basically, after we get this global model, given the current status of the vehicle, its location, its speed, then we know what's the next heading angle accelerations. So this is basically what this global model is used for. Then so this is the objective functions in this such systems. Basically include two parts. First is the communication part, is RSMA. Second is the control, Pro2 control. We want to minimize the objective functions. Let's first look at the first part, the communication part. The first part is the latency for training the global models. So here Q, QT, QH, QZ, QU, Q, WU. So they are the weighting factors for different metrics. The first part is the latency for the federated edge learning downlink. So we want to minimize the latency. The second part, the summation over gamma k. Gamma k is the estimation error of the average channel gain. So basically, we want to minimize the CSI changes and the power consumptions. So this is the communication path. We want to ensure the reliable and efficient communication. We want to minimize the latency. Also, we want to minimize the CSI changes and the power consumptions. The second part is control. First is the deviation of the reference status. So ZKREFT, that's the reference state of the case vehicle. So we want to minimize deviation of the status of each vehicle. Want to drive this status as close to the reference state as possible. Then we also want to minimize the control input effort, and also want to minimize the control input rates. So we combine all these together. We want to optimize these overall objective functions for communication and control, to jointly optimize the communication and the control, to minimize the communications for latency, for CSI changes, and the power consumption. For control is mainly to stabilize the control system. So this is a constraint. First is the transmission requirements for unicast message. So basically, for each for vehicle K, it's the CKT is the data rate in the common data stream for transmitting vehicle K's message. PT is the data rate of the private message transmitted for the vehicle K. So they are together has to be larger than the minimum the threshold for user K. And this transmission rate for multicasting message, this is what I mentioned before. C0K is the broadcasting message. The data rate for broadcasting message, CKT is a portion per message for vehicle K in the common data stream. So they are together has to be larger than the common data stream. This ensures that all the users can recover the common data streams. Okay. Then transmission power constraint. Transmission power of the vehicles must be less than the overall transmission power, and the data transmission requirement for the global models. So this ensure the achievable data rates is large enough to transmit the global models over the broadcast channels. So this is the platoon control. The models we use a vehicular kinematic bicycle models. So XKT is the longitudinal position of the case vehicle. That's the position in the x-axis. This at time t+1 equal to, so the position at time t+1 equal to the position as time t plus the VKT is the speed times the, so we project the speed over the x-axis, then times the t. Then Yk is the position at the y-axis, t+1 equal to Ykt at time t plus the vehicle projected on the y-axis times delta t. Then Ykt is the hiding angle of the case vehicle equal at time t+1 equal to the hiding angle at the time t times the rotating angle times the delta t. And the Vkt+1 is the speed at time t+1 equal to the speed at time t plus the Akt is acceleration times delta t. And another constraint is the collision avoidance. We assume that Zkt is the state of the vehicle, case vehicle, ZUT is state of vehicle U. So we assure any two vehicles, there's no common states. Okay, there's no collisions. And the original problem is makes the integrate a discrete and continuous optimization problem is NP-hard problem. So to solve this problem, we use a block coordinated descent. It's basically kind of alternating optimization problem, decomposed into two problems. One is for RSMA, one is for the Pro2 control problem. So basically for this optimization problem, we decompose into two sub-optimization problems. So we first fix the parameter of RSMA optimization problem, then we optimize this platoon control problem. Then we fix a parameter of proton control problem. Then we optimize the RSMA. So it's a kind of alternating optimization problem. We fix the parameter one optimization problem. We optimize another sub optimization problem. Then we fix the parameter of the optimized the sub problem. We optimize another sub problem. So basically, we just do alternating optimization between RSMA optimization and the protocol optimizations. And we decompose into two sub optimization problem. First is for the RSMA downlink sub problem. One is for proton control sub problem. These two problems still not convex. Then we use for RSMA sub optimization problem. We use a successive convex approximation. This is a first order approximation to convert this non-convex into a convex problem. For proton control sub problem, we use a model predictive control. So basically, to control the vehicles, the heading angle, the speed, acceleration, to adapt to the road conditions. So this is what I mean. The block coordinated distance is basically, as I mentioned before, is alternating optimization problem. So this is as I mentioned before, we divided into two sub problem. One's RSMA sub problem, one's the proton control sub problem. We fix parameter for one sub problem to optimize another sub problem. So we do these alternating optimizations. So basically, such alternating optimization can only achieve the global, cannot achieve the global optimum, can only achieve the local optimum. And also, as I mentioned before, for RSMA, it's still, even we do this alternating optimization for RSMA sub problem, still not convex optimization. It's not convex the optimization problem. So we use the first order lower approximation to transfer the original non-convex problem into the convex problem. Yeah. And for the proton control, it's quite complex. So instead of solving the proton control problem over the whole time horizons, so we divided into the different slices along the time horizons. So basically, we only do the control optimization for each the time block for each time slot. Now let's look at the simulation setup. We compare three weight-way communication sub problem. One's RSMA, one's the SDMA, multi-use linear pre-coding. One's the NORMA. And the motion of the proton follows the highway standard in the United States with the real physical limits of actual vehicles. And the estimation of GSIT follow the model in this reference one. And the fidelity agile learning computing model use the model in this reference file. So here we consider two scenarios. So for each scenario, we assume there are three lanes. So each lane there's some vehicles. We have a left lane, a central lane, and a right lanes. For the first scenario, we assume this obstacle in the left lane and the central lane. Okay. So basically, these vehicles on the left lane and vehicle in the central lane, so they have merged into the right lane. When they merge into the right lane, you have to ensure when they merging, they do not collide with the other vehicles originally traveling on the right lanes. So basically, when you control the vehicle in the left lane and the central lane to avoid obstacles to merge into the right lane, at the same time, the merging when these vehicles are merging from left lane, central lane to the right lane, they should not collide with the vehicle originally traveling on the right lanes. So this is the user scenario one. This is a problem in the scenario one. In the scenario two, so you have three lanes. Left lane is turn left, right lane turn right, and you have a central lane going forward. So basically, the vehicles in the left lane and the right lane, they have to merge into the central lane in order to going forward. Okay, you can see here you have the dashed line and the solid lines. So according to the traffic laws, when this vehicle, they change the lines from left lane to the central line, so they can only change during this dash lines. They cannot cross this. When they do the line changes, they cannot cross these solid lines. Crossing solid line for the line changing is not allowed. Okay, you can do only the line change due to this the dashed lines. Okay, now let's look at the simulation results for the scenario 1. So the 6 figures. Figure 1 shows the motion trajectory. So here you have the lead vehicle traveling on the red line, and the follower vehicle traveling on the following vehicle FL1 vehicle 1 traveling on the central line, following vehicle 2 traveling on the left lanes. So basically the vehicle 2 vehicle 1, they have to merge into the red lines. So this is the motion trajectory. So you can see this the vehicle 2 and the vehicle 1 they successfully merge into the red line without colliding with the other vehicles. Okay. And the second figure is the hiding angles. Hiding angle. So you can see for vehicle 1, vehicle 2, both need to first turn right, then turn left in order to do this merging. Okay. So this is the hiding angles. Figure C is the velocity. You can see in order for vehicles to merge the line in scenario 1, so all the vehicle has to change their speed. They cannot maintain the same speed. When they change the line, they have to reduce the speed in order to enable such merging without colliding with the other vehicles. And figure D is the accelerations. For acceleration, you can see it's below zeros, means the speed is reduced. And the vehicle figure E is the steering angles, a steering angle for the follower vehicles and also leader vehicles. And the last one is the sum rates. For RSMA, the multi-use linear precoding and the norma. So you can see the horizontal is the time, vertical is the data rate. You can see RSMA achieve the highest data rates, so they can finish the transmitting the broadcast message first, then earlier than the multi-use linear precoding and norma. This means RSMA finish transmission of the broadcast message earlier than the MU, LP, and the norma. And then once they finish broadcasting the transmission message, they only need to transmit the private message. So then this followed by multi-use linear precoding. They transmit the broadcasting message earlier than the norma. So the norma finish the transmit broadcast message the last. So when they come to transmit the common data stream, the private data stream, sorry, when they come to transmit the private data stream, they all have the same data rate. And this figure shows the latency for fidelity model trainings. So this black one, so this the first one shows on the perfect CSIT, the latency versus the set of platoons. We have 3 vehicles, 4 vehicles, 5 vehicles, and 6 vehicles. So you can see for RSMA achieve the lowest latency. Then second one is MULP, and the norma is the worst. Okay. And the A is for the case of a perfect CSIT, and the C is for imperfect CSIT. For imperfect CSIT, so you can see they follow the same trends. RSMA achieve the best, achieve the lowest latency. Then the norma is the highest latency. But the gap is bigger compared to the figure A. This means the RSMA is more robust, more reliable under the imperfect CSIT. And the figure B and the figure D shows the delay latency, downlink latency versus the transmission power. When you increase transmission power, then you can increase the transmission data rate. So this will reduce the latency. Okay, and follow the same trends. So RSMA achieve the lowest latency, and the norma is perform the worst. Also, the gap under imperfect CSAT become larger for the case of imperfect CSAT. This means RSMA is more reliable on the imperfect CSAT. So this is the scenario, the results for scenario 2 is the same. So you can see for vehicle 2, the merge into the central line. Vehicle 1 and the leader vehicle are all merge into the central lines without colliding with each other. The figure A is the motion trajectory. So you can see they all successfully merge into the central lines without colliding with other vehicles. And the second is the hiding vehicles. You can see the first for the vehicle 2, first need to turn right, then turn left. And the figure C is the velocity. So you can see in order for these mergings, the velocity speed has to be reduced. And the figure D is the accelerations is less than 0, means the speed is reduced. And the figure E is the steering angles, and the figure F is the sum rate. It's the same. So RSMA finished the transmission broadcasting message first, then on other multiple set schemes. So this is the motion of vehicle on the sum rates in the Rini vectors. So you can see in the Rini vectors, it has same performance in the scenario 1. So this is the for scenario 1. So you can see in the Rini vectors still achieve same performance as in the normal vectors. This means the proposed scheme is quite reliable even on the Rini vectors. So this is a convergence analysis. We use the BCD. The optimization problem, as I mentioned before, BCD is kind of alternating optimization problem. So this convergence gap and the iterations. So you can see the system converged in 2 iterations for BCD. For ICA, success they also converge in 2 iterations. The last one's for model prediction controls. Converges in about 5 iterations. Yeah. Okay. So the right time. Let's come to the conclusions. For this work, we jointly designed communication, computing, and control for Internet vehicles. So basically, it's non-orthogonal unicast and multicasting based RSMA. So basically, as I mentioned before, broadcasting multicast is to multicast the global model to all the vehicles to update for model trainings, and unicast for each vehicle to control each vehicles. And we demonstrate such a system is performed better than other multiplexing schemes, and can reduce the latency, can ensure the safe operation on the vehicles in Internet vehicles. Yeah, thank you.
Thank you for your nice talk, Professor Li. So in the chat box, we have one question. So I think you already mentioned this in the talk, but can you answer this question? How can we share about the convergence of the proposed alternating optimization approach and
okay, thank you.
Get a local optimal solution at the end?
Yeah. So basically, as I mentioned before, we this kind of alternating optimization problem. When we do alternating optimization problem, we decompose into 2 sub problem. For one's for RSMA, one's for proton control. So when we optimize RSMA, we fix the parameter of proton control. We optimize RSMA. So once we optimize this RSMA, the objective function will be reduced. Will decrease. Okay, then we fix the optimize the RSMA parameters, and then we optimize the proton controls. So after this optimization, the objective function will be further reduced. So we ensure for each operation, for each iterations, the objective function will be reduced. Okay, so this will gradually achieve the local optimum. Since this non-convex optimization problem, we cannot achieve the global optimum, but we can achieve the local optimum. Yeah, thank you. I hope this answer your question.
Yeah, thank you for your answer. Yeah, is there any? Okay, so Lina, yeah, asked one question. So thank you, Professor Lee, for the very interesting talk. On page 43, the latency difference
Yeah,
among
okay.
different strategies diminish as a transmit power increase. May I know the reason for that?
Yeah. The reason is when you increase the transmission power. So when you increase the transmission power, basically you can transmit more information within shorter time. For example, the global model, for example, the global model, if we want to transmit the message, the B, the size of this global model is fixed. So if you increase the transmission power, then you increase the link capacity, then the time taking to transmit this message will be reduced. So this is basic ideas. So for example, if you transmit a video of fixed size, if you increase the transmission power, so the link capacity will be increased. Then time for transmitting these videos will be reduced. And so it's the same principle. So you have a global models, the same, the fixed size. So when you increase the transmission power, the link capacity will increase. Okay. When you increase the link capacity, then the time taking to transmit this global model will be reduced. That's the reason why you increase the transmission power, then the downlink, the federated learning latency will be reduced. Yeah.
Okay, thank
Yeah,
you.
Lina, hopefully this answers your question. Yeah.
So we have 2 more questions. So thank you for your presentation. I wonder what was the length of the horizon for the MPC experiment and how many decision variables are there?
Oh, okay. This, yeah, this are very detailed questions. So can I refer this to I don't know. Shengyu, Shio, are you online?
Yeah, hello, Professor Lee. I'm online.
Can you? I need to delegate this difficult question to Shengyu and Shio. Can you answer? You know, what's the length of the horizons for the model predictor control for in the simulations? Then how many decision variables are there? Yeah, variables I can answer. I think there are 3 key variables. One is the control status and the control input. What's the length of the horizons in the simulations? Yeah.
Okay, thank you, Professor Lee, for giving us the opportunity to cooperation in this work. And, he has provided many valuable suggestions for these questions. I would say that each time slot is set to 50 milliseconds, and we use 5 time slot for time horizon and slicing the original problem into the suboptimal problem, and which can be efficiently solved and enables the dynamic control for the vehicular platform.
Okay. Yeah. Yeah. I hope this answer your questions. Yeah.
All right, thanks. The last question would be, I have one question about the federated learning part, how to do the model aggregation, OMA based or NOMA based or RSMA based.
Yeah, okay. Thank you, Dale. So basically, just let me go to that. So the model aggregation is basically just the do the average. That's for that. So this is for the model aggregation. For same as the conventional, the federated learnings. That's for the orthogonal multiple size. For non-orthogonal multiple size, so we do it in the similar ways. I think in this work we haven't considered over-the-air computing. So if we can consider over-the-air computing, the model aggregation will be slightly different. Yeah. So here we just do the average. Just do we get the gradient from all the follower vehicles, then we do the average. Yeah, that's basically the federated learning model aggregation process. Yeah.
Okay, thank you, Professor Lee.
Thank you, Dale.
All right, so is there any question from audience? So maybe let me ask you one small question. Maybe can you go to the simulation part?
Yeah, just a second. Which figure?
Oh yeah, here I mean maybe
keep-
previous one. Yeah, maybe
oh,
this.
this one. Yeah.
Yeah, 42. Yeah, here. I mean the code for the sum rate. So the RSMA actually encompass other two techniques, NOMA or SDMA, right? But
Yeah.
it seems that in some very small reason, RSMA doesn't is degrade their performance compared to other NOMA or SDMA. I mean, although it looks very small range, but I mean in this reason, it RSMA had lower performance than NOMA.
Oh no, that's the maybe I think this not show very clearly. I think that basically this shows for model trainings. So for RSMA, because it can achieve the higher rate, so it can finish these model trainings earlier than others. So once they finish the model trainings, then come to transmitting this private control information. They all say yeah.
Okay.
So they finish earlier because it has a higher capacity. Can finish all the model training earlier. Yeah.
Okay, thank you. So maybe, yeah. So last question would be, I have another question. When you implement the MPC part, how to deal with channel information of the future? Should we treat them as a constant or static information?
So Sheng, you can you answer this question for MPC parts, the channel estimation? Yeah.
Yeah. But for the MPC parts, we fix the parameters of the risk splitting communication and optimize the motion of the vehicles, so we choose this as constant information to dynamically control the vehicles. And if you can see that in our system, there is some emergency module. This is also for to avoid the sudden accident of the vehicular motion. So in autonomous driving, the safety driving is the most important thing. We may reduce or we will spare some more capacity of the communication to satisfy the motion control of the platform. I hope this would answer your question.
All right, thank you. So I think, yeah, you answer every question of our audience and including me. So yeah, if there's no more question, yeah, I'm really thank you for your nice talk, Professor Li, and yeah, so
yeah, thank you, Professor Xin. Also, thanks again for the invitations. Thanks all the audience for your time, also for very interesting and inspiring questions. So if have any further questions, feel free to contact us. Yeah, thank you very much.
Thank you.
And also please visit the RSMA webinar website to access the slides and the video of this talk. Thank you.
Yeah, thank you. Thank you, Anu. Thank you. Bye-bye.
Thank you, Professor Li.
Have a good day. Bye-bye.